Look closely at any modern house being built or torn down, and you will find a hidden nervous system running through the walls. Take away the drywall and the timber, and you are left with a massive, interlocking skeleton of synthetic pipes holding the structure together. For centuries, builders relied exclusively on organic materials like wood or elemental metals like iron. But wood eventually absorbs moisture and rots, and iron relentlessly oxidizes into rust over time. To bypass those physical limits, we engineered a completely new category of building supplies. This source text highlights the foundational definition of plastics. They are man-made materials designed specifically to be shaped and molded into many forms. We created the ultimate building material because it effectively ignores the natural decay process. Once plastic is cast into a mold and set, it stays in that exact shape indefinitely. But the exact chemical traits that make these materials so flawless for holding up a house are the exact reasons they become a massive problem once that house is finally demolished. When we examine modern plumbing, heavy cast iron pipes have largely been replaced by polyvinyl chloride, widely known as PVC. Builders adopted PVC rapidly because it weighs a fraction of what metal does. Most importantly, because it contains no iron, it is completely immune to water and will never rust. Then we have polymer resins. A resin is essentially a synthetic, sticky liquid used to permanently fuse different building materials together. These resins start as a fluid coating, painted or sprayed onto a vulnerable surface. As they cure, they crystallize into an impenetrable plastic shell that shields the material underneath from moisture and physical impact. By engineering these specific traits, rust immunity in pipes and hardened liquid armor on surfaces, modern construction detached itself entirely from the fragile, naturally decaying materials of the past. Not all plastics are created equal. Their life cycle depends entirely on their thermal response, which is a material's chemical memory of how it behaves when exposed to extreme heat. One major category is thermoplastics. You can heat, soften, and mold these materials into new forms repeatedly without losing their core integrity. Because they survive multiple heating cycles, items like plastic bottles and PVC pipes are easily recycled and reused. On the other side of the thermal divide are thermosetting plastics. When these materials are heated and molded for the first time, they undergo a permanent, irreversible chemical change. You simply cannot melt them down again. However, that permanent hardening makes them exceptionally strong and highly heat-resistant. Building codes mandate these specific plastics for high-risk applications where temperatures spike, like electrical plugs and light switch covers. The underlying chemistry of a specific plastic dictates exactly what happens at the end of its life. It either melts down to serve a new purpose, or it remains forever locked in its original manufactured shape. That locked-in durability creates an immediate crisis the moment a building is scheduled for demolition. Because these materials refuse to break down naturally, we have to figure out where the debris goes. One common disposal method is incineration. However, burning chemically complex plastics drastically alters the surrounding atmosphere. This excerpt strictly outlines the dangers of burning plastics. Igniting these materials releases heavy smoke and toxic gases that directly pollute the air and trigger widespread human health problems. If we don't burn them, the standard alternative is to truck the waste into landfills. But burying plastic doesn't destroy it. It simply transfers the problem out of sight. We are dealing with a massive timescale problem. A single discarded piece of plastic will sit in the earth for centuries, slowly leaching chemicals that poison adjacent land and local water tables over time. As this final document shows, combating this buildup requires 3 mandatory logistical pillars. We have to systematically reduce the amount of new plastic we use, physically reuse existing materials, and mandate strict, highly regulated recycling pipelines. If we want to keep utilizing the incredible strength and durability of synthetic materials, comprehensive waste management and recycling have to be integrated directly into the initial blueprints of every modern building.